Okay, again, let's have a look at some examples to see how quickly you can get the internal force diagrams and reactions without using software. I'm showing these two examples right here. So one of them does not need to use the equilibrium method uh, to get the reactions. You can use the graph method just to draw your bending moment diagrams first, and then based on your bending moment diagram, you can derive your reactions quickly. So this is the case of what I'm talking about. The other case on top right here, from an experience that you would need to do equilibrium equations. You can sum up your um, sigma f y equals 0 and a moment at one point is 0, and you can work out reactions first, and then based on your reactions you can draw your bending moment diagrams. Let's start from here right now. So I'm going to say this is a y, and here let's be y. All right. And I got a UDL over 2 meters, and I convert it into a point load. That's 4 times 2. 4 times 2. Oh, sorry, let's say this sigma at M point A is 0, and the moment clockwise is positive. So I've got 4 times 2. That's the point load times the lever arm is to here. That's 1 meter here. So 1 plus 2 kilonewtons. The lever arm is 3. And minus 4 times by equals 0. And in this case, you can work out your by is 3.5. And then so you can work out your ay. Let's just erase this. And then you can work out your ay is, the overall is 10 kilonewtons minus 3.5. That is 6.5. You can use the sigma y. If y is 0, 10 minus 3.5 is 6.5. Okay, and now next we draw the bending moment diagram. So so how do we start with this? So what I do is I've got a 6.5 point load acting at the end of the beam and to a length of 2 meters, and I also got 4 kilonewtons in UDL that are acting at the same length. So what I say is that, okay, I've got something like here, something like this, right? But that is UDL that is counterbalancing my trying to press it down, right? I'm trying to tilt it up, but this thing is trying to press it down. So it's a counteract to my point load bending moments. So my point load bending moment is at 6.5 times 2 is 13 kilonewtons, right? 13 kilonewtons meters. And my UDL here is omega L squared over 2. And that is, how much is that? That gives me 8 kilonewtons meters. So it's counteracting my point load. So that is end up being 13 minus 8, and I got 5 kilonewton meters right here. So this point here is 5. And then I just connect a straight line to here. And this portion here, that is 2.5, because it's the middle point of the triangle, 5, 0, 2.5 in the middle. And for the point load acting in the middle of the beam, the moment is PL over 4. So I'm going to say this is something like that. Okay? So this is not scaled quite well. It should be lower than that, because say, so this something like this. Okay? So this portion here, there's a PL over 4. There's a 4 times 2 divided by 4, that's 1. This bit of distance is 1. So the overall moment 2.5 plus 1 is 3.5. So this is your bending moment. It's done. So 3.5 here, 5 is here. So the overall this beam is compression at the top, tension at the bottom. Done. Let's jump onto this one. For this job here, we don't need to do this reactions. We can just draw using the graph method to just draw quickly and based on the bending moment diagrams, we can derive the reactions. So let's start from the cantilever end. Let's start from this end here. So point load acting at a meter of 4 meters distance. The bending moment is PL. Let's quickly get 4 times 8 is 32. And right here we've got a UDL, and our bending moment is going to smooth curve. So that is omega L squared over 2. That gives 48. 6 times 4 squared over 2, that's 48. So we can connect those 2 points together. So 48, 32, the midpoint here, that is 40. And because at the middle of the point there's a point load, so the moment acting at the midpoint is PL over 4. So the P is 10, L is 10, divided by 4 is 25. So it's a positive moment of 25. And there's a negative moment of 40, so it's counteracting each other. So negative 40 plus 25 gives negative 15. Let's say right here, straight line. So right here, that is a negative 15. 25 is right here. This distance here is 25. With minus that gives the actual bending moment is 25, because there's 10 kilonewtons is trying to pushing down the beam, because otherwise the whole beam is hogging like that, and this 10 kilonewtons is pushing down, so it's counterbalancing this moment here. So it's got a negative 15, a depth here. All right, so this is how we're going to draw the bending moment, and then from this point on, we can quickly get the reactions now. I'm going to use in the triangle method. So this is 8 kilonewtons. I'm going to say this is 8 as well, because this point load is only acting on the right hand side of this reaction. But you can also use the moment divided by the distance, because the shear is the derivative of the moment. So you can use moment divided by the distance. 32 divided by 4 is equals 8. On the right hand side, there's another triangle here. We need to work out what's the vector here. So 32 minus 15, that is 17. And 17 divided by the moment divided by your distance is 17 divided by 5. That gives 3.4. So we're going to say 3.4 is on the left hand side. Okay. So the BY reaction overall is 8 plus 3.4 is 11.4 kilonewtons. That's your reactions at the BY. And your AY is simple, straightforward. So overall, you can use sigma y is 0. And sigma y is 6 times 4 plus 10 plus 8 is 42. 42 minus 11.4 gives, that is, AY is 30.6. Done. See how quickly you can get the internal force diagrams and reactions. Sometimes you need to work out the reactions first, but sometimes you don't. From my experience, the pattern that I see is, excuse me, is that when I have a solid triangle, and I know I can, starting from the solid triangle, to get the reactions, because when you have a solid triangle, your relationship with the bending moment and shear force is linear. So you can use, because remember that your bending moment is the integral of the shear, and your shear is a derivative of the moment. So when you have a relationship that is linear, that you can quickly, just using the moment divided by your distance, gives your reactions. So this is a really good example that to do some practice on. So the more you do it, the quickly you can spot your bending moment and internal force diagrams. Then you will be quickly to work out your reactions. All right, that's it. Thanks for watching.